All right, let's jump right into this explainer. If you've spent, any time studying networking, you've probably heard one of the absolute most pervasive myths out there. It's this idea that if you bundle two 1 gigabit links together, you just instantly get a 2 gigabit pipe for everything you do. I mean, it sounds perfectly logical, right? 1 + 1 = 2. Well, today we are going to shatter that misunderstanding together. We're going to look at exactly how EtherChannel distributes traffic and why that 2x speed assumption trips up so many network engineers. Here is our game plan for today. We'll start by unpacking the EtherChannel speed myth, then contrast packets versus traffic flows. After that, we'll decode the load balancing hash, talk about dealing with uneven traffic, look at topology and redundancy, and finally, verify your configuration. So, Section 1, the EtherChannel speed myth and why 1 + 1 doesn't always equal 2.
I want you to picture a scenario. You've got PC-A sitting on one switch, and it needs to copy a really massive, high-resolution video file to server A on another switch. You've gone ahead and bundled two 1 gigabit links between these switches. So does that single file transfer actually get to use 2 gigabits of speed? Take a second and really think about your assumption here. It's a classic case of expectation versus reality. Our expectation is that the switch is going to act kind of like a casino card dealer, right? Tossing one packet down cable A, the next down cable B, basically splitting everything perfectly down the middle. But the technical reality is entirely different. A switch splits traffic flows, not individual packets. It absolutely insists on keeping a single conversation, like our massive file transfer, locked onto just one physical link. Which means your file transfer, it's maxing out at 1 gigabit.
Moving right along to Section 2. Packets versus traffic flows, and why this switch won't just split the difference. It really all comes down to timing. You see, different physical cables can actually have these microscopic differences in how fast they transmit data. So if a switch sent packet 1 down the first link and packet 2 down the second link, well, packet 2 might actually arrive at the destination first. When packets arrive out of order, the receiving device has to scramble to reassemble them. And worse, TCP, Transmission Control Protocol, interprets out-of-order packets as network congestion or packet loss. It will literally throttle your connection speed to compensate. So the switch makes a really calculated trade-off. It sacrifices perfectly even balancing to keep your traffic stable, predictable, and totally in order. So what exactly is a traffic flow? Well, simply put, a traffic flow is just a single, continuous conversation between devices. PC-A talking to server A, that's one flow. A laptop browsing a web page, that's another. A backup server copying data to a storage array, yet another. The switch doesn't look at individual packets in a vacuum. It focuses entirely on these overarching conversations. All right, Section 3, the load balancing hash and how the switch decides where traffic goes. To make this decision, switches use a mathematical hashing algorithm to pick a cable for each flow, and they rely on specific data to make that math work. At layer 2, the switch might look at the source or destination MAC address. At layer 3, it can use the source or destination IP address. And on some of the more advanced platforms out there, at layer 4, it can even use TCP or UDP port numbers. Now, generally speaking, using both the source and destination IP addresses is going to give you the best variety for the hash algorithm. Why? Because if, say, 50 computers are all talking to the exact same server, the destination MAC or IP is identical for all of them, but their source IPs are all completely unique, which gives the mathematical hash exactly the variety it needs to successfully distribute those flows across different physical links. Let's look at Section 4, dealing with uneven traffic. And hey, don't panic, it's not broken. This is where things get really interesting, because more flows do not automatically mean more bandwidth usage. The switch's hashing algorithm isn't actively measuring the real-time file size of your data. It just places the flows. So you could theoretically end up with link 1 carrying just a single traffic flow. But if that flow happens to be a massive multi-terabyte database backup, link 1 is going to be totally maxed out. Meanwhile, the hash might have placed 10 different tiny web browsing flows onto link 2. 10 flows versus 1, yet link 2 is barely breaking a sweat. The counters might look wildly uneven, but trust me, the EtherChannel is functioning exactly as designed. Section 5, Topology and Redundancy. Let's look at EtherChannel, VLANs, and spanning tree protocol. Here is an absolutely crucial mental model to lock in. Spanning tree protocol's entire job in life is to prevent network loops. Normally, if you plug two switches together with multiple cables, STP will just block all but one to stop a loop. But when you bundle them into an Ether channel, STP treats that entire bundle as one single logical forwarding path. It basically turns a blind eye to the individual cables. This leaves the switch's internal hashing algorithm to quietly and efficiently handle the distribution of flows across those physical member links right behind the scenes. And because STP sees the bundle as one link, it gives us incredible resilience. So what happens if, say, a backhoe cuts one of your fiber lines, or a cable just randomly gets unplugged? Step 1, the physical member link fails. Step 2, the switch instantly notices and recalculates its hashing algorithm based only on the remaining active links. And step 3, any traffic flows that were using the dead link are seamlessly moved over to the surviving links. Sure, your total aggregate bandwidth drops, but your logical connection stays up, and your network survives the failure without a total outage. Pretty awesome, right? All right, Section 6, verifying your configuration. Trust but verify. If you only remember one single command from this entire explainer, make it this one: Show EtherChannel Summary. This is your ultimate health check. When you run this, you are looking for two very specific letters next to your interfaces. First, you want to see a capital U, which confirms the port channel is up and actively in use. And then, next to your physical interfaces, you want to see a capital P, which proves they are successfully bundled into that port channel. Honestly, if you don't see those exact flags, your Ether channel just isn't working. Once you know the bundle is actually up, you run Show EtherChannel Load Balance. The big takeaway here is that this command removes absolutely all the guesswork. It reveals exactly which mathematical hash the switch is currently using. Are you balancing based on destination MAC or maybe source and destination IP? This command tells you straight up, preventing you from guessing blindly when you are deep in the weeds trying to figure out why traffic is flowing the way it is. Before we wrap this up, let's rapid fire through some really common beginner mistakes so you can confidently avoid them. Mistake 1. Thinking one flow uses all links at once. We know it doesn't. Mistake 2. Assuming that 2x total capacity means 2x speed for a single file transfer. It definitely doesn't. Mistake 3. Looking at uneven interface counters and assuming the whole bundle is broken. Mistake 4. Using a load balancing method like destination MAC when literally all your users are talking to one single server router. Mistake 5. Forgetting that a massive data center switch has very different hashing capabilities than a small branch switch. And finally, mistake 6, configuring it and just walking away without running those verification commands we literally just talked about. To really anchor all of this, I want you to keep a specific metaphor in your head. Think of the port channel like a multi-lane highway. By adding lanes or physical cables, the highway gets a much larger total capacity. It can accommodate hundreds of different cars or traffic flows simultaneously. But each individual car, it usually stays inside one single lane from start to finish. You get this massive aggregate capacity, but you aren't making a single car drive sideways across 3 lanes at the exact same time. So we've completely busted the 2x speed myth, and we've mapped out exactly how the switch distributes traffic, flow by flow. But here is my final question to leave you with. If the load balancing logic finally makes perfect sense, are you ready to master what happens when it all goes completely wrong? What exactly do you do when the math fails, a misconfiguration happens, and a port channel interface gets suspended entirely? Keep this knowledge fresh, because troubleshooting those complex Layer 2 failures is exactly where you'll need to apply it next.